Hello, I'm Chris Ambrose. This is going to be your virtual lab experience for the Alka-Seltzer Lab. So I'm going to give you a little bit of background on the lab. I'm going to run the two experiments and provide you with some data. So this lab is all about Alka-Seltzer, and we know that when you put Alka-Seltzer in water, it fizzes. So it's producing a gas, and the gas that's being made is carbon dioxide. Now, what a lot of people think is this chemical reaction is caused by the fact that the tablet itself is reacting with water, but that's actually not true. Alka-Seltzer has three ingredients in it. Here they are. Alka-Seltzer has aspirin in it, so that's used to alleviate headaches. That's an acid. It has citric acid in it that can help with stomach upset, and that is, wait for it, that's an acid. The third ingredient that's in Alka-Seltzer is sodium bicarbonate, otherwise known as baking soda. So you probably have some of that in your kitchen. Well, that's a base. Now what happens with the tablet is when you put it into water, the two acids in the tablet react with the base. And one of the products is carbon dioxide. And it makes it all fizzy, and that's what you drink. Here's the reaction that just happened. So here's the sodium bicarbonate, that's its formula. Reacts with acid, it makes carbon dioxide, water, and then some kind of salt. What's important with this chemical equation is the ratio of these two. That's going to come into play later. This is a balanced chemical equation, so that means the coefficients next to everything are 1. So therefore, for every 1 sodium bicarbonate, we make 1 carbon dioxide. And that applies to moles. 1 mole of that makes 1 mole of that. So that's going to come into play later. So here's how this is going to work. The goal of this experiment, there's actually 2 of them, is number 1, how much sodium bicarbonate is in the tablet altogether? And then the second experiment is going to be looking at how much sodium bicarbonate gets used up when it reacts with these 2 acids here. Because right now in this beaker, there is some leftover sodium bicarbonate. Now, why is that important? It's important because the leftover sodium bicarbonate that's now dissolved in water, you drink, and that will neutralize extra acid in your stomach. And if you have an upset stomach, it can help to make it feel better. All right, so here's how the setup is going to work. This is the apparatus that you're going to see in a second. What we've got is, this is where the reaction is going to happen. It's going to produce carbon dioxide. That's going to go up here into this middle flask. This is filled with water. And what it's going to do is the carbon dioxide is going to exert pressure. It's going to force the water out, and it's going to get collected into this beaker right here. Now we're going to make an assumption. We're going to weigh this water after the reaction's done, and we're going to convert it to volume. We're going to make the assumption that the volume of water produced is equal to the volume of carbon dioxide used. And we're going to use that in the ideal gas law. Okay, so here's the setup right here. All right, so on the left you have, that's where the reaction is going to happen. You see there's an Alka-Seltzer tablet in there. And in the middle, that's where the water is going to get displaced, and that's where the water is going to get collected. So this first experiment has hydrochloric acid in it. The reason for that is it provides a large excess of acid so it can totally react with the sodium bicarbonate in the tablet. The second experiment here, so I have another setup, has got, in this reaction flask, I still have a Alka-Seltzer tablet, but now all I've got is water. So what's going to happen is the acids in the tablet are just going to react with the sodium bicarbonate. There's no excess acid in this case. It's the acids in the tablet that are the limiting reactants. All right, so I've weighed out everything. So if you can flip to your data table, this is going to be page GL9. Here are the data. Now, there's a couple of parts that you don't have to write in, so I've put that in with an X. All right, so what I'll do is kind of zoom out a little bit, and what you can do is maybe pause the video for a second and get all of these values down. Go ahead, pause it. Did you pause it? And we're back. So we've got all our masses written down. I've got a mass of the whole tablet. I've got a mass of half tablet. I have a mass of the empty beaker over on the side. That's what these represent. I also put a thermometer in the water and got its temperature, and that's going to come into play later. We're just going to assume that the temperature is the same for both. And then finally, I took the barometric pressure. So this is in torr, named after the inventor of the barometer, Evangelista Torricelli. And currently it's 746.8 torr. That's equivalent to millimeters of mercury. Okay, so here we go. So what I'm going to do is initiate the reaction by tipping over this little vial that's inside. And once that happens, what we're going to see is the water will collect over in the beaker there. All right, so here we go. Just tipping it over, making sure it totally reacts. You can see that the water is filling up there. Just going to swirl it around, get that going. Try to make sure all of that gets mixed up with the acid. And I'm basically just going to let it run until it's done. All right, so while that one's going on, I'm going to also start this one to save some time. Okay, and I'm just basically going to let these run. A little piece in there, so just bear with me for a minute. You could always fast forward, but I'm just going to let this video run until it's done. Okay, and I can tell if it's done if the water stops coming out. So it's still dripping out, so that means the reaction's still going on, still making carbon dioxide. You can see the water is getting displaced. And over here, we're still going, still bubbling away. And let's check this one. All right, that looks like it's done, I think. Let's see. Yeah, I'm gonna call that done. Let's see if this one's done. Yep, I think that's done too. Okay, so it's a little tricky one-handed, but I'm gonna put a pinch clamp on here. There we go. Okay, gonna weigh my water. Remember, this volume of water equals the volume of CO2 produced. All right. 394.11. Okay, so that's gonna go over here. 394.11. And I'll let you do this next part. You can calculate the mass of displaced water. And then you use the density to get the volume of water. And remember, there's 3 sig figs here, so you're going to have to cut off some of the numbers you have here. All right, let me go get the other one. Come with me, won't you? All right, pinch clamp. There we go. There's there. Off we go. Now see, there's less water in there. That makes sense because, remember, we reacted all the sodium bicarbonate there, not all of it there, so we didn't make as much CO2. 28651. Grams. Now this is going to be down here. This is going to be in, whoops. This is going to be grams. This is going to be converted to milliliters. Same thing here. This is going to be grams. This is going to be converted to milliliters. All right. Now the next thing you have to do is convert to Kelvin. You're going to use the ideal gas law, so that's what that is there. All right, I'm just going to run through the calculations a little bit, and then you should be ready to go. So on the next side, you're going to use Dalton's law to calculate the pressure of carbon dioxide gas. So here's Dalton's law. The total pressure is the pressure of the barometer equals the pressure of the CO2 plus the pressure of water. The reason that's there is because when you do a reaction over water like we did, you have to account for the fact that some water vapor is there and is going to exert a pressure. So the way you find that pressure of water is you flip to the back of your lab manual. And what you'll see is there is a table. There's my bookmark. There's a table. This shows you the pressure of water over different temperatures. It ranges from 15 to 30 degrees Celsius. So let's see what temperature we had. We had 27.8. So the way you use this is you go to the 27 degree row, there it is, and it was 0.8, so 27.8, you go to the 27 row and the 0.8 column, There's our pressure, 27.9. Okay, you go back here. So this is going to be 27.9. And that's in torr. It's the same unit. You don't have to do any pressure unit conversions in this lab. All right, we know that. We know that. We can calculate that. For the next calculation, sometimes CO2 can dissolve in the liquid. And in this container, there was some water. And we want to account for how much CO2 we might have lost and then add it back in. All right, so in the experiment 1, I had 5 milliliters of hydrochloric acid. That's how much acid was in there. In the second one, I had 20 milliliters of water. For every 1 milliliter of solution, we lose 0.8 milliliters of CO2. So you need to figure out how much CO2 you lost and then add it back in to the volume on the previous page, the volume of CO2, which is really the volume of water. So you get this number, and then you basically add it to the volume of water from the data, and that's what goes there. All right. Now, the next calculation, you're going to calculate the moles of CO2 using the ideal gas law. PV equals nRT. So here's the equation, and here's where everything comes from. The pressure that you're going to plug in is number 1 right here. Whatever you get here, you're going to plug in as the pressure right there. For the volume, it's going to be whatever you get right here and right here. So you're doing this calculation 2 separate times for each experiment. So right here, it's actually not the data. It's actually number 2C. That's the number right above. So you do it for experiment 1 and then you do it for experiment 2. You're doing this calculation 2 times. That's why there's experiment 1 and experiment 2. N is moles. Moles is the unknown. R is given. It's this value right here. This is the value of R when the volume's in milliliters, the pressure's in torr, and we have moles in Kelvin. Finally, the temperature must be in Kelvin. So you got to use the Kelvin temperature here. So you're solving for N. And again, just to re-emphasize, you're doing this calculation twice. You're doing it for experiment 1 and for experiment 2. You're going to have 2 separate values of moles. Okay, on to the next page. This is where you're going to calculate the grams of sodium bicarbonate. So here's the chemical equation again. Remember, it's a 1-to-1 mole ratio. So whatever number of moles of CO2 you have, which is from the previous page, you're going to then say that that's the moles of sodium bicarbonate. They're the same number because they react in a 1-to-1 ratio. Once you have moles of sodium bicarbonate, you can convert it to grams. That's the molar mass of sodium bicarbonate. So in this problem here, just like in the last one, you're doing the calculation twice, and the goal is to get the mass of sodium bicarbonate for experiment 1 and experiment 2. For the rest of these calculations, it should be pretty self-explanatory as to what you have to do. So I won't go through all these little steps here. Okay, so what you're going to end up passing in is this page right here. You're going to start with page 9. You're going to pass that in all the way through the post lab, page 13. The post lab should be fairly straightforward. It's just this page right here. Shouldn't take you very long. What you'll have to do here is you locate an Alka-Seltzer box or any tablet pack. Just Google the ingredients of Alka-Seltzer, and it should give you the active ingredients and their amounts. So you can just look that up on Google. And you're going to use those numbers for down there. One of the questions here has to do with error. It says, during your experiment, you notice that the gas delivery tube is not securely attached to the flask, thus resulting in lost CO2. So basically this is saying, this is airtight, and this is saying, well, what if it's not airtight? What if some air leaks out? There's a lot of places air can leak out here. It can leak out of the place where the glass tubing goes into the stopper. It can leak out over here. There's another stopper there. There's a lot of places where the CO2 can leak out. So if it leaks out, it's your job to figure out what measured value that would collect. So we were doing this situation here, and you need to think about what we were collecting and what that would affect. Other than that, the rest of these should be self-explanatory. There are No questions on the back, just want to point that out, okay? So this has been your virtual lab on Alka-Seltzer. Again, you're going to pass in from 9, make sure you keep track of your units and your significant figures, all the way through 13. Thank you very much.